Okay, for question 3, actually we did this before, but anyway, I'm quite surprised that most of you got into so much trouble getting this correct. So anyway, the clue to solve question 12a is actually on the fuse. So we learned that whenever you see a fuse, it is the live wire. So because of that, you should know that your live wire is X, and in any 3-pin plug, the top pin hole is actually for the longest pin, and the earth wire as a safety device would need to be engaged first, and therefore it will be at the longest pin. So because of that, if you look into that, this will be where the longest pin goes in, and hence your wire Y will be the earth wire, and this leaves the neutral wire to be Z. Okay. Okay, B, I'm quite, I created question B to check whether you are aware about the power loss has to come from the current, right? Power loss is dependent on the current. So number one is that when you look at this question, you need to be aware that each of these refrigerator, whether there are 4 of them or 1 of them, they are operating normally. So in order to figure out how much current is drawn by each refrigerator, you need to rely on the power rating. So the first step to solve this question is to actually find out how much current each refrigerator is drawing. So because of that, you can use your power formula P equals to VI. The power of each refrigerator is 2000, as shown on top over here, right? And because you should also know that your power extension is actually made up of parallel connection, so that if one is broken, the other sockets are still working. So because of its parallel connection, if the main is getting 220 volt, all of this socket is going to be able to supply 220 volt to each refrigerator. So because of that, you can just substitute 220 volt over here, and you can find out that the current that each refrigerator is drawing is about 9.0909 ampere. So if you think about it, then if this is your main socket, and then after that you are going to branch out to 4 refrigerator, right? Refrigerator 1, refrigerator 2, refrigerator 3, refrigerator 4, and each of them is drawing 9.0909 ampere, right? So you have this case versus this case, whereby it is just one of them. So now the question is asking you how much difference in terms of power loss. So the other thing that when we set this question, we want to check is that student aware that this power loss happened in the wire, right? So if you think about it, where is the wire? The wire is this one and all this, right? Correct or not? These are the wire. So if you imagine the wire will take up some of the power, then your circuit over here, this illustration become, you will have your EMF over here, right? Then through the wire will have certain resistance, and because of this resistance, some power is lost, right? So your power loss comes from the wire's resistance. So this box represent the wire's resistance, and then after that, it branches out to your 4 refrigerator. Right, then after that, this whole thing returns to the first, right? So the thing is that I want to find the power loss over here. And to find the power loss over here, I can use either P equals to I square R, or I can use P equals to V square over R. right? And this power loss is the power loss in the wire. So I want to find the power wire, I of the wire, out of the wire, power of the wire, V of the wire, out of the wire. Now, there are still some of you who try to use this to find the power loss in the wire. The problem with this is not that it cannot be used to find power loss, is that you do not know what is the PD across the wire, right? You know the EMF is 220 volt, and this 220 volt is going to be divided by the wire's resistance and the refrigerator, right? So we do not know, right? We do not know. We do not know how much voltage is being used, right? But as long as we are concerned, we know that the current here is 9.0909, and each of these is drawing 090909, 9.0909. So what does it mean? It means that we know exactly how much current is going through the wire. It's 9.0909 times 4. So with this information, I know about the current that is flowing through my wire. And from the question, I also know that the resistance of the wire, sorry, let's use another color. The resistance of the wire is 0.5. So we also know this value. So because of that, right, most of the time when we are calculating power loss, we would use I square R, simply because we do not know how much voltage is being used up by the wire. So because of that, to solve this question, we know that each refrigerator is drawing 9.0909. Then, in the case of one fridge, well, the power loss in the wire will be, I will be equals to 9.0909, I square R, sorry, right, multiplied by 0.50. And then after that, if I have 4 fridge, then the power loss in the wire will be 9.0909 times 4 square. Do I need to multiply the resistance of wire times 4? No, right? Yeah, you still the same wire resistance, so it is still 0.50. Right, so because of that, once you find this difference, which I think this will give you 41.322, and this will give you 666.156, you will be able to find that the difference in power loss is, you subtract the two, will be 620 W. Yeah, so that would be how you solve this 3-mark question. As for part C, actually we want to be quite strict on this. We want students to actually let us know where is the heating up. Some of you says that the fridge will overheat. No, the fridge is drawing the right amount of current, the right amount of voltage. So the fridge will not overheat. Where will it overheat? Well, it's the part whereby it is drawing the most current, right? Which is at the socket or near the wire at the socket. So because of that, actually in the original draft of the answer key, we will only give this 1 mark if student says that it will heat up and the overheating will happen at the wire. So we actually want to see the keyword overheating at either the socket or the wire. Right? Some of you in your answer, you say it will overheat the fridge. Is actually wrong. We actually should have taken away your mark. So we want to see that there's overheating at the socket, or that it will basically heat up the wire, which may eventually cause a fire. Alright. Okay, then for part D, although it is a very long context, basically, we are just trying to see how well you can adapt to an overwhelming of data. So down here is actually quite straightforward. What happened is that the the vapor, as it goes through the compressor, it will basically it will become vaporized. I mean the coolant fluid, after it goes through the I think it's pump or compressor, I forgot. Yeah, it will vaporize, and basically we are asking you how much energy will it takes in. So in this case, it's just your latent heat of vaporization equals to mass times specific latent heat of vaporization. One thing that you may need to be mindful is that we have purposefully given you units that is not matching, so you need to convert your mass into kg. So your mass should be 0.050 kg. Your specific latent heat of vaporization, there's a kilo there. So actually you need to be mindful that this should be like that. And that's it. It's an easy mark to get. If you do all the conversion, depending on how you calculate it, you may get this value, or you can also give me 142 joules per gram, depending on how you what unit you try to standardize. Okay, then for part 2, why it feel warm? Basically is because if you read the context, the vapor after it reaches the back of the thing, it actually start to condense. So we actually want to differentiate students who are able to read the context and realize that, oh, when the coolant fluid reaches the back of the refrigerator, condensation actually happens. And if condensation actually happens at the back of the refrigerator, then condensation is actually a process that will release thermal energy, right? And because it releases thermal energy, that's why our hand feel the warmth. So here we would want to see that the process condensation actually happen, and that when condensation happen, it basically releases thermal energy, which is being felt by the hand.